Hey students, I got another question here. It's about this hard one again. It's from let's see, chapter 17. Now it's from the harder book, which is also though chapter 17, and so it's on sound waves here. Let's see, it's problem number, well, I'll put it on here, 139. All right. And so let's read it together. It says two sound speakers are separated by a distance d, each sounding with a frequency of f. An observer stands at one of the speaker and walks in a straight line a distance of x. All right, so I'll take this as the observer. And the observer is going to move to here, some distance x. Okay, so the observer stands at one speaker. All right, so I'll say, okay, here is speaker number one. So maybe speaker number one is on a pole here. Okay, so an observer stands one speaker and walks in a straight line a distance x perpendicular to the two speakers. They could have done a better job kind of explaining this. But I think they're trying to say you've got these two speakers that are separated by some distance. And so I got to make it vertical because when they say perpendicular, I need to go, horizontal. Yeah, I guess the author was complete. At first I was thinking maybe the author didn't say enough, but you can set up however the person walks, and most people walk horizontally. So I'm going to say, okay, the person walks horizontally a distance x, and it is perpendicular to the two speakers. So I think they're kind of implying here the line between the two would have to be then perpendicular to the direction they walk. And so it's kind of like a tall pole where the two speakers are separated by a distance d in the vertical direction, and then I walk in the horizontal direction. And it could be the other way around as long as it's perpendicular. I guess the speakers could be laid out horizontally, and you'd have to walk, like climb a ladder, a distance. Anyways, this is probably the best way to kind of visualize what they're trying to put here in words. And that might be part of the hard problem, is trying to kind of say, okay, what are they trying to say here in these words? Okay. But here's the physics part of this. Until he comes to a maximum intensity of the sound. And so this has to do with the interference. And so if we have one wave, and we have another wave coming from another direction, you get constructive interference. You get maximums when the two crests, and then as they flow, it'll be the two troughs, and then it'll flow, and then it'll be the two crests, and then, and then so as long as they're lined up. Crest is lined up with crest, and trough is lined up with trough. And that would occur when one of them travels exactly one wavelength further, or perhaps two wavelengths further, or three wavelengths, or four wavelengths. So it doesn't have to be an exact answer here, but we do know that we get constructive interference when crest lines up with crest. So they have to either be exactly the same length, no wavelengths between them, or one or two or three. And so the way they say it, until you get to the maximum, I think they're saying until they get to the first one. Because if you kind of redraw this picture, and I'll just kind of put it like this, S1 for speaker number one, and S2 for speaker number two, and the observer over here. The distance from speaker number one to the observer is our x, which then, because this vertical distance is d, this distance from the observer to the second speaker is the hypotenuse of a triangle. And so using Pythagorean's theorem, that is, the sum of the square of the legs equals the square of the hypotenuse, we can see that the distance of speaker number 2 is a little bit further. So there's no way that they can be the same distance. So it can't be 0. And then as we get further away here, there'll be some kind of distance, between them. And I'm wondering if we give enough information to say how many wavelengths. And so I'm going to go here with lambda, 1 wavelength. This could be said a little better, but let me continue on for the gist of the problem. So what they're trying to say here is that the distance, the square root of x squared plus d squared minus x has to be a number of wavelengths. And you know what, I'm going to, because I don't think the author said it real well, I'm just going to put an integer here. And so let me put n wavelengths, okay, where n can be a 1, a 2, a 3, or 4, and just kind of open up to some more possibilities here, okay, because they're going to say, how far is he from the speaker? And so here I'm solving this for x, or trying to solve it for x. I can write it as n lambda plus x, and then the square root of x squared plus d squared. And then I can square everything. So squaring the square root gives me x squared plus d squared. And this looks like an a plus b squared. So it would be a squared plus 2ab plus b squared. And therefore that x cancels off. And then I will get a d squared minus an n squared lambda squared when I move this over. And then I have a 2n lambda x. And then finally, solving for x, I would have a d squared minus an n squared lambda squared all over 2n lambda. And I think that might be the best answer. You can kind of see here that one option is n equal to 1. And I have a feeling that's what the author meant in this problem. And so one of the spots, I'll call it x1, would be d squared, and then if I said n equal to 1, minus lambda squared over 2 lambda, would be one of the possibilities of where it is. Now, before I go any further and do n equal 2 and talk about it, I should probably point out there's kind of an unspoken rule in all of these problems that if they give you numbers, you should put numbers into the answer. Well, they don't in this problem. And I think that even goes without saying. Most students realize that right away. They go, okay, yeah, they gave me numbers, and so I have a little formula. I got to put the numbers in to finish the problem. But another unspoken part of that rule is your answer should be listed in what they gave you. And the reason I bring that up is they talk about in the problem the velocity of the sound and the frequency, not the wavelength, and that's what I have in my formula. And so I'm going to come up here and remind you that velocity is wavelength times frequency. or put another word, wavelength is velocity divided by frequency. This would look better if we then wrote it as velocity squared over frequency squared for the wavelength squared. And again, velocity over frequency here. And I suppose we could even go further and simplify this. So maybe I will. I could multiply top and bottom by frequency squared, so I don't have these compound fractions. And so x1 would be, let's see, across the top I would have the d squared f squared minus v squared. And across the bottom I would have a 2v, and one of the f's but not the other would cancel. So this might be what the author is after, although it wouldn't surprise me if the author left it like this in a compound fraction. I would be very surprised if the author is taking that as an answer, because it's got the wavelength in it. But also, I think the author is kind of implying number one, but I think number two should also be kind of discussed, because this, again, like this one here, you would have a d squared minus, and now if you have a n equal 2, you would have a 4 lambda squared over 2 times 4 lambda. But maybe, again, I'll kind of do what we did up here. This should probably be written best as d squared minus 4, and we would have like a v squared over an f squared here. And then this could be written as an 8, and then we would have a v over an f. And again, we can simplify it, but I think I should probably not go further and just say, at some point, this isn't mathematically valid, because at some point, this term right here is bigger than that one, and we're starting to talk about negative numbers. So when I set this up and said it would be an integer number of wavelengths, 1, 2, 3, 4, there would be some maximum. And that maximum, of course, would then occur when, this is still positive. So, in other words, so long as n squared lambda squared is less than d squared, or n lambda less than d, okay, then we have a solution. But once we get into high enough n values, we don't have a solution. Of course, it's possible there's no here solution for that matter. There could be a place where you never have far enough. In other words, if d is really small, if these two speakers down here in my drawing are really close together, if they're less than one wavelength right here, as you walk away, the difference between these becomes less and less. In fact, you can kind of see when you're really far away, the distance to one speaker and the second one are nearly the same. So the most difference you can get is when you're right in front of speaker number 1. So there is some maximum. Now, that being said, I think that's why it would be the observer stands at one speaker and walks in a straight line a distance d perpendicular to the two speakers until he comes to the first maximum of the sound. Yeah. Anyways, I think I covered it. So I wish the problem was better described, but I think we're looking here for this kind of covers, I think, the physics the author's trying to get at. All right, take care.